So the next one is B6, right? So B6, one of the ones that I had the wrong thing in the key. And I'll talk about like how I got that incorrect answer that was posted in the key, too. And that's because it's probably one where a few people probably got that answer. And so it's a bit tricky because you have to think about things. So in this case right here, right, what we're looking at is essentially, dissolving ammonium nitrate in water, right? And so this is a reaction that is endothermic, right? So it requires, the reaction to take in heat from its surroundings. And that's, how, a lot of those like cold packs and stuff like that, how they actually work is that because they're endothermic, right? They're taking in heat from the surroundings. That means that other things are going to get cold in those cases, and because it's absorbing heat, so some other stuff has to give off heat in those cases. So anytime you touch anything that feels cold, what's happening is that there's a heat transfer from you, right, who's the warmer thing or the thing that has the heat energy to whatever it is that needs that heat, right? So like the process of melting ice, right, is endothermic, right? So that's why ice feels cold, is because it's like pulling heat away from you, right? Same thing then like on, the other direction when something feels hot, right? Your body's pulling the heat away because it's warmer than you. And so, right, so it's trying to reach that equilibrium and everything. But, right, and that's, then how like heating packs work, right? Is that they're an exothermic reaction, right, that are releasing heat and your body's then absorbing it in those cases, right? Just slight aside. So, right, so in this problem right here, right, we're given the reaction, right? So ammonium nitrate solid forms ammonium nitrate aqueous that has a delta H of reaction of 25.7 kilojoules per mole, right? So that's what the delta H, the enthalpy of dissolution is in this case. And so in the problem, what we have is that we're trying to find out, what the final temperature is, right? So TF is what we're looking for. And so we have a cold pack, right, that contains 50 grams of ammonium nitrate. We dissolve that in 125 milliliters of water. And then the solution has an initial temperature of 25 degrees Celsius, right? So TI is 25 degrees Celsius. And no heat transfer between the cold pack and the environment, right? So we're considering the heat pack and like the solution that we have, right? It's a completely insulated system, so we don't have to worry about losing any of the heat that's generated from that reaction to the surroundings, right? All of that heat is going to get transferred into the solution that we have in these cases, right? And so then the last piece of information that we get is that the specific heat of the solution is 4.184 joules per gram degrees Celsius, right? Right, and so that's the specific heat of water, and so we're just making an assumption here that that specific heat is going to stay exactly the same in that case, even though, right, we're going to be dissolving ammonium nitrate into it, and that's going to be influencing what goes on. So in terms of the way to set up this problem, right, what we want to look at is twofold, right? So in terms of what we're looking at, right, is we're going to have Q, right, of our reaction, right, is going to have to then be equal to negative Q of the solution, right? So the amount of heat that's being given off by the reaction has to be absorbed by the solution, but it's going to be in the opposite sign then in that case, right? Because if one thing is going to increase in heat, the other thing has to then decrease in heat. And so the thing to then approach, right, is thinking about, okay, well, what does Q of the reaction equal, right? So in this case right here, right, we know that we have the delta H of the reaction, so the Q of the reaction is going to have to equal, right? So we can consider this to be happening, right, because it's in solution. We can consider this to be happening at, constant pressure in this case. And so we can, assume then that this is going to be equal to delta H, right? That's what that reaction is going to just simply be the enthalpy. And so the delta H in this case, right, for that system is just simply going to be the number of moles times the delta H of the reaction, right? So because, our reaction is in, per mole, right, kilojoules per mole, we want to go strictly energy in this case. And so now all we have to do is just simply multiply the delta H of the reaction by the number of moles of ammonium nitrate used to figure out how much enthalpy, what the enthalpy value is of that specific reaction, and that'll give us then what Q of the reaction is in this instance, right? So what we have to do now is convert 50 grams of ammonium nitrate into moles, right? So if we're looking at the number of moles, right, that's just simply going to be the mass of the ammonium nitrate divided by, right, NH4 NaO3 divided by the molecular weight of it. Right, so the mass is 50.0 grams, which is a lot. Divide that by the molecular weight. So I'm just going to go do the math, right? So nitrogen is 14.01 plus 4 times 1.01 plus 14.01 plus 16 times 3. That comes out to 80.06 grams per mole, right? So the grams are going to cancel, and so mole will end up on top. So we get is 50 divided by 80.06. That comes out to being 0.625 moles, right? So that's how many moles that we have of this reaction. So now, right, to get the Q of the reaction, we just simply multiply the number of moles we have. So 0.625 moles, multiply that by the delta H of the reaction. So that's 25.7 kilojoules per mole, right? Moles cancel. What we get is 0.625 times 25.7 comes out to 16.1 kilojoules, right? So that's how much energy has to be absorbed by the reaction for this transformation to happen. So we now know what what Q of the reaction is, and so now, right, if we want to get what the Q of the solution is going to be, right, so that's just simply, right, Q of the solution is equal to negative Q of the reaction, right, opposite sign. So in that case, right, that just simply becomes negative 16.1 kilojoules. Now, one thing I'm going to do to make my life a little bit easier, right, because the specific heat is in joules, I'm just going to convert that kilojoules into joules, right? So that just simply comes out to being negative 16,100 joules, right? So that's the heat of required of the solution, or that's going to be transferred into the solution, or sorry, not transferred into, right? That is going to be taken from the solution in this case right here. So we have that value. So now what we can do is set up, right, what the equation looks like for the Q of the solution, right? So the Q of the solution is just simply a calorimetry style problem, right? So all it is just simply taking the, this equation right here, right? So the Q of the solution is going to be equal to the mass of the solution times the specific heat times the change in temperature in this case right here, right? So that's how we get what the Q of the solution is, right? We just simply multiply those, right? So there's one difference always to pay attention to, right? The specific heat is always going to be the mass of the system, whereas in the case of molar heat capacity and stuff like that, right? Those are always going to be, right? Another way that you can refer to specific heat, right, is also a specific heat capacity, right? But molar heat capacity, right, then is then per mole of the system, right? So you always have to be careful that you're making sure that you're using the right units for everything, right? And then some things don't even have a molar heat capacity, right? They just simply have a heat capacity because it's already been standardized, right, for whatever that mass and that material is in those cases, right? That's usually something that happens for alloys, right, where you have a bunch of different elements or something that are a part of like a kettle or a calorimeter or something, and in those cases, right, you can't really by eye necessarily weigh it and then be like, okay, right, like this is using a table, you figure that out, right? Like those are things that you have to standardize. And I think we're going to do that next week with the bomb calorimetry problem. But in this case right here, right, we don't have to worry about that. Now, looking at this right here, right, what we have is a few different things, right? So we know what CS is. Delta T is what we're trying to figure out, right? So if we just write out what delta T is again, right? So that's mass times CS, and then that's just going to be simply, right, temperature final minus temperature initial. In those instances. So, right, so that's what we get right there. So we know what CS is. Now the mass, right? And so this is the thing where the original answer that I had posted to Canvas was off because I used the wrong mass, right? And so if you're looking at it very quickly, you're going to think that we're just simply talking about the mass of the water in this case, right? Just the pure water, right? And so 125 milliliters of water, right, is the same as 125 grams of water, right? Because, the density of water is 1 gram per milliliter. The tricky part is that the solution is going to contain the ammonium nitrate as well, right? So at the end of the day, like, you're not going to have a mass of 125 milliliters that you have to take into account, right? It's going to actually be a mass of 175 grams of solution, right? Because those 50 grams of ammonium nitrate, right, are going to be part of the solution and everything. And so, the thing to think about, right, is that you have as your mass, right, is 125 milliliters of H2O, right? And then that is going to get converted into grams, right, by 1.0 grams per milliliter. And then you're going to add to that, right, the 50 grams of the ammonium nitrate. So that comes out to 175 grams, right? That's what the mass is. And so if we do that math, right, what we have is Q of solution, in this case now, is going to be equal to 175 grams times the specific heat, right, which is 4.184 joules per gram degree Celsius, right? Comes out to, actually, I'm jumping ahead because I want to probably rearrange this equation easily for myself so that I can get what the, because I want to solve for final temperature, right? I don't know what that is. So if I rearrange this equation, right, to get to the final temperature, what I have is, right, so if I rearrange this, what we get is Q of solution over mass times the specific heat is equal to final temperature minus temperature initial. So if I move that around, right, what we get is final temperature is equal to temperature initial plus Q of solution divided by mass times the specific heat. And now that I can plug in everything that I have. All right. And so one thing, I think there was a question on Piazza in terms of being able to use degrees Celsius versus Kelvin and all that stuff. Right. So you can't really use Fahrenheit for any of these because the Fahrenheit scale is not on the same like linearity that degrees Celsius and Kelvin are, right? Degrees Celsius and Kelvin, they're the exact same scale, right? They, you go up 1 degree Kelvin, you're going up 1 degree Celsius in those cases. The only difference, right, is just that for Kelvin, right, there's no zero value, there's no negative value. Whereas in the case of degrees Celsius, right, there can be up to negative 273 degrees Celsius, right? Because they move the same way, right? So 0 degrees Celsius equal to 273 Kelvin. And so that's why you can just essentially, right, for in the case of like delta T's, for the most part, you don't have to worry about switching them around and getting concerned with them in those instances, right? Because they're just, for the most part, going to match directly and scale. Actually, they always will. Right? Because if you just subtract temperature initial and you're going to like -5, right? All you're going to do is convert that into 5, and that gets added up. Anyways, but back to this right here, right? So that's why I'm not worried about converting this into Kelvin, right? I can keep it in degrees Celsius. So, so if I plug in my numbers now, right? So temperature final is going to be equal to temperature initial, which is 25 degrees Celsius, plus Q of the solution, which is negative 16,100 joules, divided by the mass. And so the mass is 175 grams times the specific heat, which is 4.184 joules per gram degree Celsius, right? And so joules cancel, grams cancel, and the degree Celsius hops upwards. And so what we get is 25 degrees Celsius plus, and so we have negative 16,100 divided by 175 times 4.184. Right, we have plus negative 21.99 degrees Celsius in this case, right? So we have that right there. So then that means that temperature final is going to be 25 plus negative 21.99, comes out to 3.01 degrees Celsius, right? So that's what the final temperature is of our solution in this case right here, which is pretty cold, right? 3 degrees Celsius, I think, is like 35 or 37 degrees Fahrenheit or something like that. Something along those lines. However, right, the next part of the question, right, is asked, like, does the water freeze? And the answer is no, right? Because you're not below 0 degrees Celsius. Right. And so that's what you get right there. And that's how you approach that problem, right? So you have to make sure that, when you're doing the masses, you're thinking about what the actual system is that you're looking at, in those cases, and how that affects, what's going on. Now, and in some instances, right, when you're doing a calorimetry problem, like an actual, like, experimental one, you're usually not using, dozens of grams worth of material to the point where it influences what the overall mass is. Usually you're going to be doing those reactions on a smaller gram scale, so that way the amount of mass that's getting contributed to your calorimeter, right, is negligible, and you don't really have to worry about and focus on those things. And usually also, right, you do a few different amounts and stuff, so that way you can do multiple trials, and you can then actually using an equation, right, by plotting, figuring out what the actual heat capacity is of something, and stuff, and like the amount of energy that's released. But in this case right here, right, you have to take into account, right, because 50 grams is close to a half of the mass of water in that case, right? So it's a pretty big increase. Now, the original value that I had posted, right, where it was like, I think, negative 5 degrees Celsius or something like that, is what you end up with. So this is all the correct one. Anybody who skips ahead and looks at this part right here, right, I'm just going to make this note, right? So this is the incorrect approach, right? So in the incorrect approach, you would only use the mass of the water in that case, right? And so if you did that, right, and you had temperature final is equal to 25 degrees Celsius plus, Q of the solution, which is negative 16,100 joules, divided by now 125 grams times the specific heat, right, which is 4.184 joules per gram degrees Celsius, right? So joules cancel, grams cancel. What you get is 25 degrees Celsius plus negative 16,100 divided by 125 times 4.184 comes out to negative 30.78 degrees Celsius, right? So if you do that now, then, right, you get final temperature is 25 minus 30.78. You get negative 5.78 degrees Celsius, right, is what the temperature change, in that regard would be. But more than likely the final temperature would be 0, because you also have to take into account, right, the amount of energy it takes to go through the phase transition from a liquid to a solid, and that usually requires a lot more energy than just simply changing the temperature of something. But yeah, so, right, and so that's, and negative 5.78, I think, is what I originally had as on the answer key, which was wrong. But it's actually, right, 3.01. So that's a slight thing, and that's kind of like, one of those, like, tricky things to think about too, right? If something kind of along this line comes up on an exam or grade scope or Chem 101, right, always kind of pay attention to what is the system in each one of the cases, right? So the solution has to incorporate also the thing that you're dissolving into it, right? Because that's going to be influencing it as well. Because that temperature is going to change. It's not going to stay completely constant of that material. Right. And so, thinking about all of those things. So, yeah. So that's how you do B6.